All right. Amazingly enough, we haven't driven everyone out of the room. Is anybody showing up just for the second session? You guys are going to be really confused. If I go into something and I kind of just skip over the fact that you weren't here for the last session and we didn't introduce it in detail, please wave your hand or make rude noises, and we'll backtrack a little bit and make sure that you have enough context to really kind of grok what we're talking about. So, for you folks who weren't here in the first session, I will actually go over this. So basically, we're going to spend the next hour or so of your lives and ours talking about designing for availability in a large-scale system in Azure. Things that we've learned from putting systems into production, dropping millions of users onto them, and seeing what breaks, and ways to work around that. So if this doesn't sound interesting, if you think you're indeed in the wrong place, I absolutely invite you to go and look at the actual slides, which are right here. Excellent. First defeated by PowerPoint already. So there are other cool things going on if you don't enjoy building large-scale services. If you do, I sincerely hope you are in the right place. Excellent. It worked! That's never actually worked before. I feel so happy. I feel so happy I put this slide in. Thank you. You've made my day. Okay, so we're going to talk about two key things today. We could talk about a lot more stuff, but we had to winnow it down to fit it in an hour. And even though it sounds like I can talk for ad nauseum, yep, there we go, I can't. My voice will give out eventually, and you will definitely get bored at some point. So we're going to talk about two key things. One is designing for availability, and more importantly, designing with the concept of failure in mind. This is foundationally different than how we approach availability in an on-premise world with capitalized hardware. So I asked this earlier, but we'll go into a little bit more detail. Who has set up SQL Server mirroring, always on, log shipping, DR? So trivial exercise, right? Cheap, too, huh? The traditional way that we've approached the high availability of highly stateful services on-premise is through the titanium eggshell method, in that we buy highly redundant, specifically configured, purpose-built hardware. And it works. We've been doing it for 30-plus years. We've gotten really good at it. But it's still complicated and it's still expensive. But we have precise control. We can do very interesting things. When we move to a shared environment, we move to service composition with varying SLAs, all of a sudden we don't have the option of trucking in the latest Dell or EMC appliance with like 18 redundant power supplies. Don't know if they have one, but it would seem a little weird. We instead have to address reliability and availability at the design perspective. We can't just bolt it on afterwards. The other part of that is this big switch from developing to operations being two completely different things, to thinking about building a service from a DevOps perspective. Is anyone in a DevOps role? I like you guys a lot. You're really important. You're going to appreciate the latter part of this. So when we think about designing services, it really is designing for operations. It's not the I'll ship a new, I'll basically go and throw it over the wall and then managing is someone else's problem. If you don't bake in insight into the system, into its health, its operations, its scale, its behavior, who's played Frogger? Do a little nostalgia check here. I knew we were in the right room because I did this I was at SQL Rally Nordic a couple weeks ago in Copenhagen, and they looked at me like I was crazy. Now, maybe Frogger doesn't translate well. That could have been something to do with it. So think about not explicitly designing for operations as putting a blindfold on and playing Frogger, or trying to get from here to the other side of the 405. It's generally not a good situation. Myself and Simon were chatting earlier going, if we had one piece of advice to impart, if we could go back a year in time and tell ourselves something other than lottery numbers, it would be the importance of reinforcing design for operations and insight. And I'll cover a little bit more detail what that really means, and hopefully share as many anecdotes as I can without LCA or marketing coming in. Okay, quick recap. For those of you who were earlier, if you're working on really large-scale stuff, there are certain things that change at this physical scale. Whether you're deploying in cloud, premise, box, on carrier pigeons, it doesn't matter. There's a lot of physics involved. Great paper by James Hamilton, written about 5 years ago, that goes into a lot of these things in detail based on the experiences of running Windows Live. This is kind of the thing that I always go back to when I think about design patterns and architectural choices. So we're going to talk about the stuff on the right here. We're going to think about designing for failure. So anyone do mobile applications or mobile services? A few hands. How many external data sources do you depend on? That is any number bigger than 0, too many. Yeah, exactly. Very large numbers of external services you both have no control over nor any visibility into their runtimes. So there's a lot of underlying components and dependencies that you can't trust. Even if you control them, you still can't necessarily trust them. So we need to think about how do we break the dependencies between various components and still soldier on when some of these things don't behave quite the way we want them to. Still avoiding single points of failure. I knew the surfaces they were very solid and robust. Dropped, kept ticking. See, that's the titanium eggshell method. If we were in the cloud, what we would have done is given you 8 really flimsy ones. Just thought that up. That's recorded now. That's going to come back to haunt me. Okay, so that's about designing for failure so that you can drop your flimsy surface, because we gave you really good ones that you can drop, not that you should, and keep on going. The other part is about instrumentation. So who, on a regular basis, will remote desktop into a machine and check some performance counters? Okay, that works great with one machine. It's pretty good with 2. If you've got 2,000, that's a bit of a problem in terms of you're looking for a needle in a bag of needles. Not a very easy exercise. Let's think about it. Looking for a needle in a haystack is easy. You just need a really big electromagnet. All problems have solutions. They just seem a little weird sometimes. Okay, the other thing is when I have all of these underlying components, I need to know about their relationships between each other. So I need inter-service monitoring, alerting, and instrumentation. If one particular service doesn't even have to go offline, it just starts offering degraded service, longer latency, less throughput. I need to know about that in order to be able to take action. I need to have my instrumentation in production give me sufficient visibility to debug. Who has different trace levels for test and production? This is how we've learned how to create software because it's so expensive to do tracing. The interesting thing when we move into operations is if we didn't capture it, we don't know it, and we can't recreate it. So we have to think about the type, volume, and channels for telemetry in a very different way. We also need to be able to do runtime configurable logging. Who has put logging trace information around configuration in web config or app config? Come on, everyone's done it. So there's a really interesting property when you're moving to Azure. What is the mutability of a deployed package? There isn't any. So what you've done in our traditional ways that have grown up and are reasonably mature is I go into my web or my app config, I put in all my telemetry information, which I then lock into a read-only package and deploy to my website. That's a bit of a problem. This is just an extension of how do I actually do configuration in a live service in a central and planned fashion. I was chatting with some folks between sessions. We were kind of musing on failure points. I'm going to talk about machine-level failure points, but at the end of the day, the organic failure point is usually the most impactful. No amount of software in the world will save you, actually, it's not entirely true, we can talk about that, but without very specific patterns, practices, and processes, there's very few pieces of software that will save you from pushing out a bad configuration. Because generally you'll go, hey, you told me all this stuff was over here, and it wasn't there, so I'm just going to sit here and whine. This is what software usually tends to do. Okay, if this doesn't sound interesting, again, the doors at the back still work. We haven't actually locked them yet. So a quick refresher on the nines, the magical nines. This gets thrown around a lot, and usually I go, well, let's pull back a little bit and actually think about what the nines mean. Has anyone ever worked on a 5 or 6 nines system? A lot of work, isn't it? How big is your operations manual? Absolutely. Yeah. Don't even think about it. Don't look at it. Don't even whisper near it. So down around 5 and 6 nines, this is when we think about telecommunications equipment. This is when we think about military and government. This is when we think about things that absolutely must run. And let's look at some of these numbers. At the bottom, 31.5 seconds of downtime a year. That sounds like kind of cool. I'd like to have that. But if you look at the actual business value in building systems like this, there's a reason we only build very few systems in the world that operate at this level. It's the critical pieces of infrastructure. And when you think about it, what they actually do is very, very constrained. Systems running at this level don't have a lot of moving parts from a logical or physical perspective. They tend to evolve fairly slowly. An ASIC in a telecom switch today doesn't really look a huge amount different from one several years ago in terms of its features and functionality. I mean, it moves ahead fairly slowly. The speeds might get much faster, but the logic and the capabilities don't change much. So when we think about business applications, it's always balancing how much we're willing to spend to get availability versus the impact and cost of downtime. So let's think about some standard Azure SLAs, basically our contract to you that we're fighting to adhere to. So in terms of storage availability, we're going to say that we're going to shoot for having no more than 10 minutes of downtime a week. Again, we don't want any, but our SLA is there might be some. So for any press in the room, I did not, repeat, not just say we will absolutely give you 10 minutes of downtime. What we're saying is our SLA is that we will not go above that. So that means that if you take a dependency on storage, I have a chance of having 10 minutes of downtime a week or 40 minutes of downtime a month. And if I have dependencies on that service, I need to figure out how to work around that. Or just go, okay, for 40 some odd minutes a month, I'm just going to put up the fail whale and go, come back later. It'll be fine. We'll take your money at some point in the future. Maybe the SQL Azure availability, compute, internal and external. But we talked earlier already about these are compositional systems. It's not I just use one thing. Very few systems just use one thing. And the interesting part about SLAs is they're, just like the systems are compositional, the SLA numbers are compositional. So if I have 5 services that I depend on that all give me 4 nines, my overall SLA is only 3. Because the more moving parts, the greater chance that one of them is going to be down at any given point in time. If you think about a data center, ours, Amazon's, whose ever, I mean, the physics are largely the same. If I put 100,000 of anything out there, some of them are always broken. Something is always failing because these are mechanical things. There's moving parts, there's heat, there's mean time before failure. The more things you have, the more chance that something is broken. But at the same time, the less chance that everything is broken. And this is the line that we're going to split. This is very different from how we think about hardening on-premise systems. Okay, so reality of physics. You get enough time, enough pressure, and enough scale, some piece will fail. So it really comes down to, as software developers, what is the response of our code, of our systems, of our approach to these failure modes? Really, we've got 2 choices. We can gracefully handle them, continue to provide business value, continue to provide value to our users, or we can do what a lot of things do, which is just put up an ugly-ass error message. And, did I say that? Oh, yeah, I just did. Too late. I can put up an error message and just go, I didn't care enough about you to even give you a nice error message. Please go away. It's doable. It's cheap. It's easy. It's not necessarily what I would recommend. So then we need to kind of break this down a little further and think about the 2 kinds of errors that we need to be able to handle. If I'm working in a system that has a large number of moving parts, some of which are constantly failing, I will have some degree of transient interruption. Earlier I said that I'd talk a little bit about how SQL Azure actually handles this particular problem. And when I go into the next one and we talk about basically approaches to working against occasionally unreliable data stores, I'll go into detail both on the physics of the underlying platform and how that surfaces up to your code. So we really have kind of 2 types. The little hiccups in the system. Nothing really bad, a couple of milliseconds, maybe a few seconds. And the systems will largely self-heal. Happens during replication and failover and basically switching load away from damaged nodes. And then there's the enduring ones. This is where basically I depend on a third-party content moderation system. There's an anecdote I can't tell you, sorry. Where I basically go out and I take my comments and my likes and say, hey, is this okay to actually put on my site? Or is someone throwing some terribly nasty words up? That site, that's a third-party service, that can go offline, and I won't know about it until it's gone. So how do I deal with that? If it's just a little hiccup and I can wait until it comes back, great, transient failure. If it's gone for a couple of days or even an hour, well, I might need to do some intervention. Do I shut off the feature of my site that requires that? Do I switch to another third-party service? Or do I queue the data and say, hey, we're going to be a delay in getting this stuff to you? And this is when we think about design, we start thinking about splitting these various considerations and doing things in a more nuanced fashion. I'm not going to pretend it's easy. I'm not going to pretend it's simple. But it's some of the things that you kind of have, if you're going to design a system at internet scale, not everybody will, these are some of the things you need to take into account. So let's talk about the scope of failures so that we can kind of tease this problem apart a little bit and think about it in a more discrete fashion. So when I think about node-level failures, this is the stuff we're generally used to thinking about. I lose a machine, I lose an instance, I have a transient connection issue between me and somebody else, I have a configuration or a code error. Now, in an on-premise system, if I'm doing machine-by-machine configuration, this is a node-level issue. In Azure, some of these are a little bit more interesting because I'm rolling out services that are composed of multiple pieces. So I have service dependencies that may fail, both internal services and external services, either inside my app, inside Azure, or something else. I'm calling out to a mapping API, I'm calling out to content generation, I'm calling out to Twitter or Facebook or any of these things. These services can fail. They don't offer 100% SLAs either. So how do we, as app developers, react to that? And here's the dirty little secret. DR exists for a reason. Data centers can become unavailable. It can either be, hey, my line to the data center got cut by an overzealous individual with a backhoe, or it can be a flood, a lightning strike, or some form of human error. Every major cloud provider, and again, this is in the news, so this is not me calling anybody out in specific. We've had them. Amazon has had them. It's an unfortunate fact. We don't want it to happen, but at some point it could. A lot of the East Coast data centers, they're not in great shape right now. Some of them are floating. So it could happen, and we need to think about if we absolutely require the ability to survive and continue to provide business value in this world, how do we architect our applications? All right. So I'm going to chat a little bit about node-level failures. So here's how SQL Azure actually handles high availability. So to get a highly available 3 nines SQL database in Azure, I go create database, and I'm done. I have a highly available database. Having stood up log mirroring and even just knew always-on stuff for a long time, that's really cool. I mean, just wow, I didn't have to do anything. It's just there. But how it does it, there's a few seams. We hope to close them in future, but here's where we are right now. So when I create a database in SQL Azure, what I actually get is I get a primary database and a couple of replicas. My database is over a certain size, I get a few more. And what happens is there's a consensus-based model on the transaction log. I commit a transaction to the primary. And I say, give me insert some data, delete some data, update, whatever. It goes, OK, I've received this data. And then it gets a consensus-based commit from one of its secondary replicas. It's not a synchronous write. It's basically a synchronous acknowledgement from one of the replicas saying, hey, somebody else has this transaction. It's safe. You can return back to the user. So it's a trade-off. We've traded high availability and determinism against speed because we had to put bits in 2 different places and get an acknowledgement. So if you have synchronous mirroring on-premise, you're paying the same, the similar type of latency cost. In SQL Azure, we kind of say, listen, you're going to go through this because we're going to give you a highly available experience because we know that at some point, if we have enough servers, we're going to lose one of them. So what happens when we lose a node or we do a failover for whatever reason? What happens is the gateway layer that manages your connection down to the databases will basically swap you over to one of the secondary nodes. Now, what happens in that case, and unfortunately this is something we really need to think about in a more coherent fashion, is we kill your existing connection and say, you need to reestablish the connection through the gateway. It doesn't happen very often, but it does happen. So if I actually consider it to be really amazing that for more than a decade, a piece of code that basically said, give me a SQL connection, was considered to be so reliable that you would never fail to be, actually, yeah, we did a pretty good job. That's pretty cool. But now we're moving to a world where we have to rediscover some of these challenges in distributed system programming. And here's an example. So we have a number of libraries, including the patterns. Anyone use patterns and practices, transient fault handler? A couple things. There's also one my team wrote called CloudFX that does a lot of service bus stuff, but it also handles kind of transient issues in SQL that basically says, listen, that's an external service. It can have hiccups. It can go down. So I'm going to create a policy in place that says, hey, if you get one of these transient errors, I'm too busy, I'm not available, I'm moving your connection, I would like you to go back and try that again. And I'll just do it once. So here's a pretty simple example of creating one of these policies to say, I want to try 3 times every 5 seconds. If it throws a transient, not an enduring error like, hey, I don't have access, or that table's not there, but more a come back later. Put it in place, and the right thing will just happen. So in general, this is one of the common techniques we see to protect against transient issues in dependent services, whether it's SQL or storage or a third-party REST API. We need to say, oh, it will account for the fact that you will occasionally hiccup. However, this technique taken to the extreme also has problems. This is why this is a design and a balance. Why is this a really bad idea? Same piece of code. Yes, actually. So what happens here is, who's familiar with how the IIS pipeline works? Excellent. I get to go off on a little soapbox again. So IIS implements what's essentially a dispatch-based queue mechanism. So by default, you get about 12 dispatch threads per core on your box. So a large core in Azure will give you 48 dispatch threads. As work comes in from http.sys, it gets dispatched onto one of these things. Has anyone ever been in the grocery store behind someone paying in pennies? At the airport with a person who doesn't know how to use the machine to get their ticket? Oh yeah, I think I see a few faces nodding. This is an example of what happens in a queuing-based system. You're moving at the speed of the lowest one. Even if you have multiple queues, it doesn't take many slow actors in the system to bind the whole thing to a halt. So what this says is, I'm serving up a web page to a user, and users have infinite patience, right? They like to sit around and wait and see the little swirly things. I'm going to wait potentially up to 15 seconds for a user to come back, plus whatever time it takes to execute the query. And oh, by the way, while I'm doing this, this whole slot is mine. Let me give you an example of what happens if you get a little bit too overzealous with not bounding your overall calls. Now, it can happen because of excessive retries. It can happen because you don't have appropriate timeouts set in your client code, or that remote services just take an exceedingly long amount of time. Don't trust client APIs. They don't always either implement or adhere to timeouts. And you're thinking, well, why don't I just abort the thread? That's fine, right? Okay, I got a few chuckles. I know who knows the context for this one. When I'm executing a task, I generally have a couple of options. I can either cooperatively cancel, or I can basically have the rug pulled out from under me. If you go and you see a long-running transaction or long-running activity in .NET, I won't pretend to speak for other platforms, but it's similar characteristics, and I say, hey, I just abort that thread. Basically what you've done is you've corrupted your app domain, and you say, and weird things will start to happen. So at that point, you pretty much need to shut down your app and restart it again. So killing threads in flight, other than saying, hey, can you please shut yourself down, generally a very bad idea. So your only approach is you have to know the bounds of your calls. Some of them do unexpected things. So this is an anonymized graph from a site outage that I was working on a couple of months ago that had an unbounded call out to a third-party service that went offline. And of course, when does stuff go offline? It doesn't go offline when there's nobody using the system. It goes offline the day you launch a new product, the day you update a new version of your site, the day 1 million people showed up and went, hey, we'd like you to be successful, but you won't let us. So what happened in this case was, at time 8, again, highly anonymized, third-party service goes offline. The proxy to the client API to reach out to it had a timeout property. And we all know once you put a timeout property on things, it just works, right? The client API wasn't respecting the client timeout. So basically what should have been a maximum 30 second, which would have been bad enough, turned into, ooh, what's that? That's a lot of minutes. And what happened was, you've got these, basically everybody started stacking up behind these. So the number of calls here is about, it actually drops off. I didn't actually put the throughput numbers here, but you can, as you can imagine, once we start to see the spike in response latency, throughput goes in the bucket. And the number of calls that we're getting through the system is relatively small. And what happened was everyone was getting blocked out of the system. Two things can happen in this particular case, at least with IIS. One is that you fill the application queue because requests keep showing up, and you'll get a 503 service unavailable. And in general, that message is not very pleasant. Basically means, I'm too busy, please go away. I'll talk about how we detect that in a second. The other piece is you have some form of front-end service that's actually proxying or authenticating in. In this particular case, that service went, requests are taking longer than 30 seconds. This service is broken. I need to block access until it catches up. So until time 22, the service was offline and basically saying, hey, I'm running, I haven't crashed, but I'm not available. This is one of the instances where throughput and availability are inextricably linked. It doesn't matter if my servers are up if I can't serve the demand that I have or gracefully turn it away. So we need to bound our service calls. We need to fail gracefully. We need to push stuff out of the queue. And we need to not trust. We need to not put extreme trust in the external services that we call. So I got asked last night when I was doing a presentation about what kind of retry policies do you use? This was largely driven from reviewing a piece of code and going, you have the same retry policy in your web handlers, your cache handler, and your database handler. This doesn't seem like a good idea. Let's tease these apart and think about the physics of the system. This is not actually guidelines. This is just some samples. This all depends on what is the business SLA that you're trying to meet. If I'm doing live page rendering, I'm going to have much tighter tolerances than if I'm doing a service call to a rich application, either a rich web application or a mobile app. So just assuming that I want to be able to, I never want to wait more than 200 milliseconds to render a page. Basically, if my backing data store slows down, I just want to give up after 200 milliseconds and try something else. I want to hit the first time. If it fails with a transient, I want to immediately try again with a couple of milliseconds delay, then maybe try twice more at 50 and 100 milliseconds with a linear backoff. If I'm doing an asynchronous work where no one's directly waiting, I might wait much longer. I might say, it's okay to wait 60 seconds. If I want to overcommit in terms of the number of parallel activities, that's fine too. But what I will do is I'll go, I want an exponential backoff. Does anyone know why?
Things don't line up.
So things don't line up, exactly. Basically, if you get enough systems, if you get enough actors trying to execute an activity in parallel, and you put them all on a linear backoff, at some point, through the magic of physics, they align. You get this nice little sine wave where everybody tries to crowd through the door at once, and then goes away, has a cigarette break, comes back, and tries to crowd through the door again. It's the same technique that Ethernet uses to prevent collision. Ethernet, as opposed to, anyone remember token ring? Oh yeah, old school for the win. Token ring was coordinated. Basically, it was a mutex that was getting passed around. So you were coordinating who was allowed to send. Ethernet is a kegger. Everyone just shows up. But there's this tacit agreement that if I can't get in, I will gradually back off and back off and back off. And it turns out that it works really well. Caching is a little different. I expect much better latency and far fewer issues out of an in-memory localized data store than I do out of something that has to touch disks in another part of the data center. So I might have far more stringent, far more aggressive retry policies here. Simple fact is, a lightweight call, I can be more aggressive than a richly contextual stream. TDS, the connection to the protocol that SQL uses, has a lot of session context. It's fairly expensive to build up a connection and authenticate and tell, describe who I am. An unauthenticated binary call over a lightweight TCP channel out the cache, very different story. So I can be a lot more aggressive about the number of connections. So just, again, a lot of nuances, just stuff to consider. OK, so just one last thing on, actually two last things on availability, and we'll chat a little bit about instrumentation. So async I/O. Who uses Node.js? You guys are cool. So one of the reasons that Node.js is really interesting and gives great density is it doesn't allow you to do any synchronous I/O. Basically, it says if you're going to do a blocking operation that goes outside the bounds of my process, you're async, my friend. I will not allow you to block wait. So even if they do have a dispatch model, I'm not sitting around blocking the queue. With the advent of .NET 4.5, woo, excellent, in Azure, the ability to do a lot more async activities without paying the agility and developer cost overhead of iasync results, which I hate. I've been burdened with those things for 10 years. goes away. So we actually, the ability to do a lot of flowing async all the way through the system becomes a lot easier. There's a little thing that even APIs that look async are not always necessarily async under load. Has anyone ever used the HTTP web client in .NET? Yeah, most of you have, even if it was hidden underneath something else. So if you actually do a thread dump, and if you like looking through the .NET framework code for fun, well, you can do that. What happens when I'm basically invoking that request? It basically, HTTP web client begin request. Looks very async. It has a begin. It should be async. What it actually does is it has to authenticate your context. And that authentication passes through a mutex, an app domain level mutex. It's a lightweight mutex. I show up, I get who I am, and I keep going. But we have one of these problems where under load, that becomes a heavily contended resource. So if you start getting into thousands of calls per second concurrent, you will bounce off that mutex. What looked like a purely async operation has now actually become blocking on a global resource. So again, these things only happen when you put the needle up to 11. But that's what we're here to talk about, things that go to 11. Come on, someone had to get that. This is Spinal Tap, yes. I will throw out the pop culture references. Sorry. Okay, and the other one is about the convoy effect. We briefly touched on that. This has to do with I have a system that's gone offline. It's offline, it's offline, it's offline. Everyone's like, hey, let me in. I want to come in. It comes back online. Everyone rushes the door and then crashes it again. If you don't have some form of graduated entry to certain dependent services, your own apps can push them back underwater. All right. So last little bit on service level failures. And so entire services will have outages. Your dependent services will fail. External services, even less reliable. So there's a couple of different options you have in your code. There's the obvious one, which is to say, hey, sorry, can't do anything for you. It's the simplest, and depending on your business model, that might actually be just fine. There are other approaches you can take, though, especially if you can play with the consistency. If I'm basically recording a stream of user activities that I want to put into SQL, and it's not there, I have options. I can queue it in memory, I can queue it into an Azure queue, or I can shift it to an external system. I'm trading the consistency and potentially durability if I'm doing in-memory queuing for both throughput and availability. Again, hey, we can't process your order right now, but we'll take it, process it later, and then send you an email. Basically, that whole shifting asynchronous acknowledgement from hey, we've got your thing, and we'll process it and then tell you. Sort of like getting a coffee at Starbucks, which I've done like twice today. All right, last item around availability, because this is the one that you don't think about, or you think about too much, or it's the one that when it goes sideways, everybody knows about it, and they're banging on your door going, why didn't you think of this to begin with? And I really hate being in that position, so I thought I'd share some of the pain and some of the stories. Simon, tell us all about what happens when data centers go bad.
So we talk really here about the notion that you need to root away from failures when these things happen. And again, if we go back to the Press Association, one of the things they did was deploy to 8 data centers. Now, there are 2 reasons for this, actually. This comes back to the comment that Mark made earlier about 2 sides of the same coin. Deploying to 8 data centers gives them some advantages in terms of latency to their users. They've got global user requests coming in. So you get some sort of performance advantage. But it also gives them the opportunity to work around issues between users and those data centers, whether that's a connectivity issue, whether it's some sort of other issue that prevents one of those data centers from being used. Now, one of the things that we can use to do this distribution is a piece of technology in Windows Azure called Traffic Manager. And Traffic Manager has a number of policies that you can specify with it. One of those policies is route for performance. In other words, I connect to the system, I look up a DNS address, and I get returned an address or an IP address that's the closest data center to me. Now, on many occasions, I've seen people make the connection between geographic location and closeness. That is not the case. This graph shows a system where there was essentially a random distribution of user requests. And if we focus on the two extremes on this chart and think about Europe, there was a reasonably random distribution of requests across Europe. Yet, if you look at the distribution of load that you see that one of the data centers gets 17,500 requests per second, and the other one gets 500. It's sort of an interesting effect. That's in a system that's just basically a data publishing system. You see other models here where you might build a system where perhaps you want to distribute load to multiple regions based on user locality. So you might have a user registration service. That service may then return you some URI that then points you at where you're going to get service delivered. Building those services and using geographic location as the locator is the absolute wrong thing to do. You need to think about network latencies, which can be very, very different than geographic location. The easiest sorts of systems to build where you can have this notion of distribution of workload are those where you're doing information publishing. You've got read-only state. There's one master copy and you're replicating it out across data centers. And this is a fairly canonical sort of approach to that. You've got a source data system and you're taking data from that and you're pushing that into autonomous services. Those services are located in different data centers. They are completely and utterly independent of each other. They share no state. That means you have to manage and monitor and care for them as separate systems. Now, we just talked, as your traffic manager can direct my traffic to the nearest data center. But it can also figure out that a data center might be unavailable through probing. Now, when we probe from the traffic manager to an Azure service, we probe through the load balancer. The load balancer will route my probing request to some random instance sat behind it, which will answer true or false to the question, are you well? There's a problem here, because if I route to a node that isn't well, then I get the answer, no, I'm not, and that whole service goes offline. There's a feature in the 1.7 SDK that enables you to implement custom load balancer probes, which enables the load balancer to take those nodes out of rotation that are unhealthy and means that you don't run into that problem.
Basically, you avoid false positives.
You avoid false positives.
All right. So we spent a lot of time talking about availability and the approaches for working around it. Still fairly high level, but the concepts are different. The concepts are the same. It's just how you apply them is largely dependent on your workload. But at the end of the day, if you don't know what your system is doing, if you don't know the load it's under, if you don't know its health, all the best coding practices in the world won't help you. It'll be like, yeah, everything's fine. It built. We shipped it. Everything's great. It's on, right? And then you find out later going, my users knew that my stuff was broken before I did. That's not a good sign. We should probably address that. So this is what we'll go into in a little bit of detail on and kind of talk not just about the philosophy and the kinds of questions you want to ask, but as well some of the patterns that our customers have used, both platform tools and third-party services, some of which are actually out in the hallway outside. So I always approach the telemetry question from the answer that I want rather than the baseline of what I collect. I usually break this discussion down into kind of 4 areas. Am I informing or am I acting? In general, a dashboard is informing. It's not directly telling me, hey, you need to go do something. You need to go fix something. It's not a pager going off saying, no, really, you do have to get up and come in. But it's in the cloud, so at least you have to get up, roll out of bed, and open your laptop. That's actually kind of cool. Unless, best to avoid that, mind you. All right, the type of question. What is the type of question that I'm asking, or I'm actually doing an ad hoc exploration through data? Monitoring is usually the answer to a well-known question. Normally, I'm always asking a monitoring question. What is the average CPU? What is the average memory? What is the average network latency or network bandwidth? These are monitoring questions that I already know I'm always going to be asking. Interestingly enough, none of those is a useful metric in terms of determining system health for a web application. But, Mark, you might ask, that's an outrageous statement. These are the performance counters that I capture every day. What do you mean they're not useful? The interesting part of that statement was actually for a web application, and it ties back to how I described the IIS model earlier. Based on that description, what's the only truly independent variable that I need to be measuring from IIS? Anybody? No, failures is close.
Request per second.
A request per second is interesting. If I see a giant dip, it might be a canary that something's wrong. Requests queued. It is indeed requests queued. And this is actually, I'll talk a little bit more because this is a really interesting one. If I talk about the Nyquist rate of a signal, would anybody other than the electrical engineers in the room know even remotely what I was talking about? It has to do with how often you have to sample or observe data in order to get information. Say I'm driving down the road. How often am I going to look at my speedometer? I should probably look at it more than I do, mind you, but I'll look at it, and based on how often I look at it, I'll have a certain model, I'll have a certain fidelity of that information. In turn, we think about the kinds of kind of very low momentum signals. If my CPU is 15% 1 second and then 22% the next minute, 1 minute and 22% the next minute, that's okay. I can make reasonably good decisions based on that. Queue depth, as opposed to other things, tends to change very, very quickly. If I get a huge flood of requests, or I get one of these convoys, I have seen an entire 120 instance website go down in less than 90 seconds. Just get crushed because of a programming error. So if I'm only measuring that value every 5 minutes, it's perfectly healthy, and 5 minutes later it's unavailable. And I'm going, wait a minute. So there's different types of signals in the system. There's different types of momentum. There's different approaches for dealing with those. We'll dive into this in a little bit more detail. But it's one of the ones I like to bring up as a specific example of not all sources of data are created equal, and usually the easy or the obvious things to measure are not always the correct ones. And the only reason I know this is because that was my system that I was running on a deployment that blew up in 90 seconds in a live event. So I feel this one very, very deeply, and I'm hoping to share some of the pain and embarrassment with you, so you don't have to go through that pleasant debrief that I had. Finally, this comes down to the next one. How much data do I need in order to gain insight? If it's a spike in the IIS application queue, I need to think in terms of seconds and minutes. If it's user growth week by week, I can look at aggregates in terms of weeks and months. Very different kinds of questions with very different momentum and very different data requirements. And there's also around partitioning the span of signal. How much data do I need for insight? If I need to look at how many users are active on my system, the overall aggregate view is probably more interesting than the per machine view, unless I'm looking to see if my load balancer policies are appropriate. That's where global computation comes in. If I'm looking at the depth of the application queue, I need an individual value. And then in aggregate, I might look at things that are in different thresholds. So it's very much it's a multifaceted data management problem that when you're running relatively low-scale systems, this is pretty straightforward because none of the values are changing that much and there's not that much data. When I have highly distributed systems running on thousands of machines with dozens of different interoperating systems, this becomes very complicated. And it's not like I can push the magical pause button in the sky, attach a debugger to a single instance, and get global truth. So this is where it comes down to designing for operations, thinking about this from the beginning, and fit for purpose, looking at different tools to solve this problem. I've seen all the customers who've gotten through this successfully. It's all been a polyglot approach. There's no one size fits all. I wish there was. I would just go use it. So we see a combination of purpose tools for monitoring and alerting, introspective diagnostics, and long-term trending. We see different systems to get different perspectives. We see baseline application logging and monitoring through things like Windows Azure Diagnostics or the Azure Portal, which I'll describe, as well as a mix of really great third-party services available on Azure. So anybody from New Relic in the room? So New Relic is here today. You can go and actually see a demo of their software. They have really great stuff. Essentially what it'll do, and this is very much supported in Azure, they'll drop an agent onto your roles, hook into the profiling API, and give you very rich information about what your applications are doing. This is not a code cost, a developer cost. This is basically a configuration change and a third-party service. And you get really interesting information about the application level behavior. I've used this on a number of engagements. I'm a big fan. App Dynamics, another one. These guys do really interesting things in terms of providing cross-instance correlation without having to build it in. Anyone ever tried to implement a correlation ID tracing system? It was a lot of fun, wasn't it? And they're looking at me going, you idiot. It was terrible. So they can't do everything, but they do actually do a really good job of correlating calls between services. So if you have really rich inter-service dependencies that are becoming very unmanageable, they have a great product and a great service. It's a little expensive, but if you're running this kind of mission-critical app that you have to have this insight, it's well worth it. Anyone ever used Optera? So what they do is they provide a tooling experience on top of Windows Azure Diagnostics that does a couple of interesting things. You get graphing and visualization, as well as alerting based on the metrics in there. And you also get some capabilities for doing dynamic scale. So look at these counter values and add or remove instances as necessary. A lot of folks using this pretty successfully and enjoying it. So we've talked a lot about how do we gather the information, how do we visualize the information, how do we explore the information. But sometimes you really want to be told something is going wrong.
So anybody use PagerDuty?
We can't actually see it's the lights, but no hands. I don't see any hands.
Anybody from PagerDuty here? No? Okay. So I have very many customers who use this. It's a really very low-weight tool for integrating those the house is on fire type alerts, the things that you want to really action, probably the enduring failures, and having then a system look at those and alert people based on their preferences, calendars, those sorts of things. So you can have many, many users registered in the system. You can set up a calendar for who's on call. You can then have the system cascade and escalate issues that are raised from your application. In fact, New Relic plugs directly into this. But you can pretty much integrate anything in here. It has an HTTP-based API. You can send email to it. And it will do things like send you email, ring you up, and read you the error message that it just popped over your phone, send you a text. And you can deal with those things, say, okay, I acknowledge that, I'm going to do something about it, or I've resolved that. You can then set up hierarchies so that if you happen to be out partying
we never do that.
When you're on call, nobody's ever done that. And maybe you should have responded to something in 10 or 15 minutes. If you don't, you can send it to your backup. So a really, really very valuable service and very, very low cost. And I'd recommend if you have that requirement, you give those guys a look.
Plus, you can also set it up to email stack traces to be read out to your buddies, just as a prank. Not that I would ever do that. So, kind of first point there's a lot of really great partners in the ecosystem that have really phenomenal services and tools for handling aspects of monitoring and telemetry. But there's also a baseline in terms of the instrumentation and data capture from your application, from infrastructure and applications. And the way the component that handles this is something called Windows Azure Diagnostics. Someone used it? Okay. Well, we'll get all hands up here eventually. So essentially what Windows Azure Diagnostics does is it takes a single box diagnostics experience and makes it a distributed experience. Essentially, it's a combination of configuration and a store and forward agent that harvests data from individual nodes and centralizes it into a common, well-schematized store, composing tables and blobs. Someone's afraid of telemetry. Oh, actually, they're just afraid of diagnostics. Okay, so a couple of interesting things going on here. Just to give a little bit of a visual diagram. Windows Azure Diagnostics is the thing that will collect your IIS logs and put them into a central blob store. Coming soon, you'll be able to basically stand up a Hadoop cluster on Azure and hit those logs and do mining with a little bit of config, and some Hive scripts. We grab Windows crash dumps. No, Windows doesn't crash, but if you do really bad things, you might force it to do so. It'll grab your user trace logs. It'll grab your system diagnostics trace events and put them into tables. It'll grab your performance counters and your Windows events and basically centralize them so you're not doing the hunt and peck instance by instance remote desktop approach. I have a kind of a bit of a perspective on this. It's not a terribly popular one. It puts me at odds with a few people. But if I ever have to remote desktop into a production system, I have failed as a developer. I have not instrumented my application sufficiently to allow remote understanding of the behavior of the system. I may remote desktop in during testing of a new build to get really, really granular information or observe the behavior interactively through a debugger. But as a diagnostics tool, if you have to fall back to logging in into an instance, your application has not been sufficiently designed for operations. And if you have even 100, or hell, even 10 instances, figuring out which one of them will give you representative data is challenging. So the out-of-the-box experience for Windows Azure Diagnostics, it has some challenges. As with anything, when you go beyond the default design point, you hit physics. And in this particular world, you hit some interesting physics. So Windows Azure Diagnostics won't give you your third-party diagnostics information. It won't give you SQL DMVs. It won't give you storage analytics. So you have a little bit of a fractured view of the world rather than a single view. Table storage. And I'll talk about how this actually scales and how partitioning works in table storage in a second. Again, you have that too many people trying to jam through the same door because the table store and the way that we write performance counter data in uses a temporally based partition. Basically, the current minute represents the partition value. If you have 120 instances running 1,000 performance counters a second, this starts to exceed the limits pretty quickly. So in general, what you're forced to do is turn down the fidelity in order to get the scale. You need to increase your collection intervals so I get my performance counters every 5 minutes. Works for some really well, doesn't work so well for others, like the queue depth that I talked about, especially in a system where you have very bursty, very dynamic load. Since it is a queue-based store and forward system, you don't necessarily get real-time immediate publishing of key alert data. That can be a little challenging as well. It's actually usually more of an issue when I'm doing kind of initial build validation. I've put a new build up. I want to just kind of see if it all works quickly because I'm impatient. I'm sure we're all impatient as well. We want answers quickly. But finally, and this is probably the one that is the most striking when you really need it, is that the destination stores are not highly queryable. Let me kind of go a little bit into what that means. So let's talk about table store. Blobs are just files. If I want to read them, I need to connect to the blob store, grab a file, parse through it. Great for bulky, batch-driven operations, not good for online querying. So Azure Table Storage is where we put performance counter data and application log data. So in general, I'm going to get 1,000 entity updates or operations per partition per table. Because it's source time based, every instance is going to be writing to the same partition in performance counter table and event log tables. So the partition key, which limits the number of concurrent writes, is 60 seconds wide. Now they are asynchronously written in bulk, but I can hit this limit pretty quickly. And there's an interesting convoy effect here as well, because if I overload my ability to write to that partition, everyone will back off and then try again. The challenge with trying again is they're still trying to get into the same partition, and the new data is queued up behind there. So it's a bit of an issue there. But there's also a flip side going, the more entities that I put in a partition, the slower my queryability. Because just like I can get 1,000 entities per partition per table in, I have a similar cap on the ability to get stuff out. So, for example, not that this is a contextual anecdote, if you trigger a bug in your code that generates 200,000 error logs per second per instance over a period of time, you can imagine what this does to your ability to get useful information out of table store. We used some fairly unpleasant language to describe when this happened. So generally, the approach that we see is to maintain acceptable read performance, we dial down fidelity. We only see error information, no info, no debug, no warning. We change performance counter collection from 1 minute to 5 minutes. We put on the rose-colored glasses and assume that everything's fine because we don't have any data that says it's not. This is not a good situation. This is not, you cannot run a large-scale system by not capturing sufficiently rich data. So given that we have this default configuration doesn't play nicely, how do we work around that? So generally what I recommend is we split data. There are things that we might need later, and there are things that we know we will need now. It's about filtering as much data, creating two channels, one important, one bulky. So I will put my high-value data directly into things like table storage, basically winnow down the frequency, so that when I go to look in that alerts table, it's things that are actionable. Now, it's hard to get to this point, but if you do, you know you're there, in that every single thing that shows up in an event log with a tag next to it creates a case, creates a work item, creates action. There's no inform, it's just act. It's very difficult to get to, and it's always a moving target, but it's the goal, it's the North Star. The other part is I'm going to capture very large volumes of data that may or may not contain nuggets, and I'll hold on to them for a certain period of time, so that if I do trip an alert, I have the information captured. If I didn't record it, I don't have it. But unless I can work with physics that gives me a cheap way to capture this, I end up spending more cycles on instrumentation and telemetry than I do on delivering business value. And that's a little challenging. So Windows Azure Diagnostics is actually very configurable. So generally what we look at doing is going, okay, I'm going to have low latency performance counters, but I'm going to write them into a file and then store and forward the file in a blob store. I'm going to take my application logs and write them to a local file and then store and forward that into blobs as well. And blobs can sustain this kind of load up to about 1,000 instances per storage account, which is a pretty big number without any issues. So and generally how we do this is you create what's called a custom data source in diagnostics, which says monitor this directory. If I put a file there, you put the file over there. So it's a configuration experience, not a coding experience. All you have to do as a developer is go, I will create local files. Does anybody use nlog? Couple hands. Log4net? Okay, I feel bad, but that's okay. Regardless of whether you prefer nlog or log4net, as long as you have a logging system that provides the ability to do rolling files, basically roll a file over to a new directory, nlog will do this out of the box. I wrote a log4net extension to do this. You can take advantage of using Windows Azure Diagnostics to handle all the hard networking parts for store and forward and keep your existing logging channels in place, but just jack them up and make sure you're doing all async writes. Just to show you an example of this kind of pattern in action. So the other thing I say is, if you call an external component, if you leave your process boundary, log it. Component, context, result, timestamp. If I call into SQL, log every call. If I call to our external web service, log every single call. If you have a cheap way to do it, it will save you when you see things like, hey, the web request latency went from 5 milliseconds average to 5,000. Who was responsible? If you don't have component level tracing, you will never know. You may guess. You may make informed guesses. You may even be right, but you won't know. And the more moving parts you have, the more complicated this is. So this is from a production system. This is part of the data access layer that encapsulates a number of things. It encapsulates the transient fault handler. It encapsulates the thing that says how many times you had to retry. If all I see are successful items, but I have huge latency, was it that I had to retry, or was the destination source just slow? I need this data. I need to have all my external APIs called with timing, so I know what their response characteristics are like. And the most egregious thing I've ever seen, who has seen code? Log exception.toString. Everyone, I'll put my hand up because I've done it. I have done this. I will freely admit in front of you all, I have done a bad thing when it comes to logging. Why is exception toString a bad way to do tracing? You do not get all the data. More precisely, you don't always get inner exceptions unrolled, and you don't get contextual information unrolled. If I take a SQL exception and say toString, I will not get the SQL error number. We should fix that, we know, but sorry guys, that's what it's like right now. If I get a type load exception, the inner exception is where the actual data is. If I don't unroll it, that's a problem. And if I make every single developer do the right thing, someone won't. So instead, have a logging framework that just takes exceptions where you set policies that unroll them and extract the data. The other thing I generally do is I split. I have a logging channel that has all of the tracing, and then I have a logging channel that only has exceptions. I do that for searchability. Nothing annoys me more than scraping through a log file, and I get these huge blotches where I had a stack trace, and it just makes it hard to search and hard to view. So what I have is a configuration in nlog. We've also done this for log4net, where I have one channel that's basically just all one-line items with little snippets of information, and another one that has all the exceptions in it, and a third file that has all the traces. So we are just about out of time, so I won't go into the... If folks want to see this, I can show it afterwards. Basically, the diagnostics WAD config and the nlog configuration to do this. So ran a little bit over on this one. I'm more than happy to finish the content afterwards. We'll be hanging around as long as you guys want us to chat, or until my voice gives out, which should be not an infinite amount of time. And happy to take questions. Everything we've talked about is covered in at least some degree in this white paper and a few others that we have under development. And all the code that I've alluded to will show up on CodePlex before the end of the calendar year, or hopefully shortly thereafter. All right, thank you for letting me borrow another hour of your lives.